Hello everybody and welcome to something I want to experiment on. It might be weird because the comments are going to be on the side, and it might be weird because you got to look at it from the side. So I'm trying to make it so I'm on the side of the comments and this is not on the side of the comments. I think this should work out a little bit, perhaps, maybe. Hello, my name is Kamikyodai. It is, what day is it today? It's Tuesday, I think the 5th of January. It is the 5th of January. 11 a.m. here in Monterrey, Mexico. And we're going to be looking at some of the mathematics beneath Islamic patterns. And of course I'm wearing my pajama pants, but you can't see that, so it's all good. Okay, so let's talk a little bit about the Islamic patterns. So, alright, before I write anything, let's talk a little bit about them. So the Islamic patterns have one foundational cornerstone, and that is the circle. The circle is where everything else comes from. So we want to talk a little bit about the circle. So the circle has something that we call the center. The circle has circumference, and the thing about the circle is that every line from the center out towards the circumference will be the same. That's what makes it a circle a circle. All the lines that go from the center toward the circumference will be the same. No matter which way you go, all these lines will be the same. That's one of the main characteristics of the circle. Another characteristic of the circle, you can, think about it however you want, but you taught this in school. I hope that you people know about this. Of course you do. We're told that this is equal to 360 degrees, right? The sum of the circle is 360 degrees, and if we cut it in half, we say that this is 180 degrees, right? Now I want to do away with this concept. Instead of, I want to tell you where this comes from, according to the research I've done, right? So, alright, so let's say we have a circle. So we have a circle, and we have a center, and now what you do is you draw a line like this that goes through the center and hits the circumference on both sides like this. And now you take the radius, you take this distance, and instead of the center being here, now you take your center and put it over here, right? So now it's going to go like this. So now you draw a circle and you go like this, right? So now you get these 2 points. And now you can do the same thing over here. You get these 2 points. So if we actually, cross these like this, we get that. So if we clean this up a little bit, let's clean this up. Okay. So we said that we had this, then we had this, and then we had this. So a little bit cleaned up, a little messy, but whatever. The idea is that these 6 points are equidistant, right? They're all the same distance away from each other. And the cleaned up looks a little bit like this. So in our system, the one we usually use, we count up to 10, right? So we can go like 1, 2, 3. So we have a column of 10s, we have a column of 1s, right? So we count up to 10, just as much as in binary, you count up to 2, 10s, you count up to 1. So when the one column overcomes 9, we write 10, right? So 1 plus 9, that's the limit. So this is like mod 10, right? This is also what that thing on your calculator means, the mod. So we can say that we write mod 10. Fucking bullshit, that truck. Alright, so mod 10. And so they, in Babylon time, so this is way, way back, they would count up to 60. So they had mod 60 back in the way west. The reason why it has to do with right triangles, and there's a very interesting thing you can read about Plimpton 322. If you want to read more about the Babylonians and their use of right triangles, with the mod 60. So that's kind of interesting, the way that the Pythagorean theorem works with this, but right now we're not caring about this. All we need to know is that they counted up to 60 like we count up to 10. So let's say that you're a Babylonian person, you represent it with this. So what you do naturally is that you think, well, if I have a unit, I have 6 units, so I have 1, 2, 3, 4, 5, and 6 units, then naturally all of them are going to count up to 60. So I can go 60, 120, 180, 240, 300, 360. So summed up, it goes 360 degrees, so that's how it goes, right? So 60, 180, 240, 300, and 360. So you can imagine that all these 60, what it means is that it's actually like 60 lines, they call them, they're not arcs, they're chords. So 60 chords that divide up and make 60 points along this division. So this is where the 360 degrees comes from Babylon, and the fact they counted up to 60. Now I want to present another way of looking at angles that's called radians. You can find it on your calculator. It usually tell you not to, calculate with radians, but it looks a little bit something like this. So if you have a circle, and again we do this thing. Let's do this thing again. Now instead of doing that with the different areas, we're going to take account of the points and we're going to connect them. So we're going to draw a regular hexagon, right? So that's the idea now. So all of these angles, all of them are the same. So this angle right here is the same as this angle is the same as that angle, same, 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 and same. So if we rearrange the angles, you can actually sort of see something interesting happening. You can take a single triangle, so there's 1, 2, 3, and there's also 1, 2, 3 inside of each triangle. So that means that if you had a triangle like this one, an equilateral, and you cut off these corners off like that, and then you rearrange them, this one we have to rotate, look a little bit something like this. We rotated it, we put it beside it, look a little bit something like that. So we take this and we simply move it, and then we end up with these three angles, 1, 2, and 3, add up to 180, or a straight line. So we can say now, at least, that we can try this at home too. You can take any triangle, you can take the corners off, rip them off, rearrange them, and see that they sum up to 180. So the sum of the internal angles of any triangle, these three angles, add them up, 180 degrees. So let's take now this as a unit measure. Instead of saying that 180, so it's a high number, we're going to do away with it, and instead we're going to write pi. So for every 180 degrees, we're going to write pi. For any triangle, we're going to write pi. That's the idea of this. The sum of the angles of any triangle is equal to pi. So that's where we're going to go. So we're saying that the full circle, I'm sorry if this explanation is either boring or whatever, but I'm trying to explain myself here. I'm trying to understand in public. So if we say the circle now, and we again divide this in half of it is going to be pi, and then when it hits here and then goes back again, it's going to be 2 pi. So instead of saying that the full circle is 360 degrees, we're saying that the full circle is 2 pi. It's 2 unit measures of going around the turn. Alright, so 2 half turns. We can say that pi is also a half turn. 2 half turns, right? So it goes a little bit something like a gear. Okay, so we've established the first formula of our thing. We said that the sum of the internal angles, so the sum of the internal angles of any triangle, of any Euclidean triangle, I must add, some of the internal angles of any, let's call it flat, of any flat triangle is equal to pi. I'm sorry if this is what the comments are, I don't know where anything is. So some of the internal angles of any flat triangle is equal to pi. So we can have this, right, any triangle. Okay, so we have our first sort of idea. This is the first sort of mathematical statement that I want to put out. We sort of deduced it from the circle. It's not a proof, but it's something we can, be reliant on just for now, I guess. But it's not a proof. I should actually clarify that. This is not a proof. And okay, let's do away with this. Fuck it. You gotta try like doing this kind of shit, because if I don't do this, then I don't practice teaching, and then whatever. Okay, so what next? Okay, so now I'm going to talk to you about foldness. So in Islamic geometric patterns, if you see my channel, you probably know what that is. So we usually write them as IGPs, right? Islamic geometric patterns, and then an S just to say that it's plural, but Islamic geometric pattern. And they usually come in this foldness description. They'll usually tell you a 12-fold IGP, right? They usually say 12-fold IGP. We usually say something 6-fold IGP. So what does this mean? What does this 6-fold, 12-fold mean? It has to do with pi, actually. So let's take a little gander here again. So this actually combines with origami quite naturally. It does combine. Again, with this shit. Okay. So now instead, so here's what I'm going to do. Every second line, I'm going to change the color of this. So I'm going to draw every second line. Where's the other marker? So every other line, I'm going to draw another color. So red, black, and then red. And then I count how many of each I have. So I have 1, 2, and 3 reds, and I have 1, 2, and 3 blacks. So then we say that this division of the circle is threefold. So this is a threefold division. The pattern would happen inside of this. So this is where the pattern would happen. Anything that's sort of, we can also take into account that it has this mirror line there. So we can put a pattern or any division or something inside of this, mirror that, and then, rotate it around 3 times. So it will go like, 1 time, 2 time, and then what the fuck? No. So 1 time, 2 time, 3 time. So it goes threefold. So this is a threefold division. So let's look at fourfold now. Oh yeah, by the way, something I did not mention, which actually has to do with foldness and the angle. So, alright, no, we gotta talk about Schlafly symbols first. Alright, so let's just look at, we're not gonna measure anything yet or nothing. So we have a circle again. Now I'm gonna divide it in fourths like this. So what would we say this? What would this be? So we're saying that every second line I have to change the color, right? So I go 1, so I have 2 blacks, and then 1, 2, and 2 reds. So this is actually more basic. So this is a twofold division. So then it goes 1 turn, so it goes like, you can put something here, mirror it, and then mirror it the other way. So 1 turn, 2 turn. But it has this character, this mirror right here. So this is a twofold pattern right here. So this is a twofold division, sorry. So twofold division. You can think of this with origami in that this is the preliminary fold. And this is where the preliminary fold comes from. You can talk about it like that. And alright, let's do one more. Let's do actually fourfold. So like this, that. And again, we do this thing where we change the color scheme of this every 2. So I gotta go black, red, black, red, black, black, red, and this guy really drives it in there, right? So I have 4 blacks and 4 reds. So this is a fourfold division. So this is where that comes from. So fourfold. One more thing about foldness that I want to talk about, and that's the angles of foldness. So you can also talk about that. So but before we get into the angles, I want to get into the Schlafly symbols. So let's just call it quits on the foldness for now. So we're going to leave a pin on foldness, and we're going to move on to the Schlafly symbols. No, this is actually Schla, with little diatheses there on the A. I don't know how that's called in English. In Spanish, it's diatheses, these 2 little points on top of the A. The Schlafly symbols. So the Schlafly symbols come in the form of brackets. I can't draw brackets to save my life. Somebody put a gun to my head and said, draw the bracket right. I couldn't do it. So we write, let's call it like this. A bracket N, and then we close the bracket. So what is N? What does N mean? So if we have a circle, N means the amount of points that are equidistant on the circle. So if we have, let's say that we have N equals, let's say 2. So what I'm saying here is that there's going to be 2 points, 1 and 2, which have the same distance from each other. Right? So if I write in N3, it will look a little more something like this. So there's going to be 3 points which are equidistant from themselves on the circle. You can write this, of course, as 3, like this. Usually, this is also understood to be a polygon. But what we're really talking about is the points on the circle. So I'm just going to write here, N is equidistant points on circle. I think this is also sometimes called P. So any equidistant points on a circle, we can put in N equals 3, and we get 3 points that are on a circle. And now we got to talk about star polygons. A little bit, maybe, perhaps not. We got to talk about the internal angle formula. All right, so we've said that the sum of the angles is going to be equal to pi. We understand that. We understand that if we add these three up, we get pi. So add them up, so we can call this angle A, let's call this angle B, and angle C. So I'm saying that, the sum of them, so A plus B plus C, first of all, they're all the same because it's simply distance. So A equals to B equals to C. And then we're saying that all of them, A plus B plus C, is equal to pi. And then if we wanted to find out what A was, because they're all the same, we can also write it as, we can just take, instead of writing it like this, we could also write it as 3A, right? Because it's three of the same. We can say this. So if we wanted to find out what this was, we simply, we can understand it simply as a unit too. So we can say that, the three of them. So you can simply say that this angle is equal to pi over 3. And that's what all of them are, because if we add them up, they add up to pi. So we can think of them as fractions. We can say like pi over 3 plus pi over 3 plus pi over 3 is equal to pi. Pretty straightforward, thing. 1/3 plus 1/3 plus 1/3 equals 1 whole. Makes a lot of sense. It works. All right, that's good. So the internal angle formula looks a little bit something like, let me take this away, rather let me take this one away. The internal angle formula looks a little bit something like n minus 2, it's 2 pi, yeah. N minus 2 times pi over n. So this is the internal angle formula for a regular polygon. So the internal angle formula for regular polygons. Oh, shit. Well, this is why we do this, right? We gotta learn to put things in order. The internal angle formula. I don't even know if you can hear me because I'm talking to the wall, so the sound is wall bounced off, so I don't know. The internal angle formula for regular polygons. I'm so anxious, I can't believe it. So the internal angle formula for regular polygons is this one. This is the internal angle formula. And if we just wanted to have the sum of the internal angle formula, we simply take away this. So then, like this, then it's the sum of the internal angle formula for regular polygons. So this will tell us, actually no, this is interesting because this one doesn't need it to be regular, simply for polygons. Internal angle formula for polygons. So the one that we had of the internal angle, actually I should write this shit. Alright, let me just get this out of the way. And we're not talking about Schlafly symbols, I guess, yet. I guess we're talking about radians now. Talking about radians and the sum of them. So no, angle summation, I guess. Not radians, I guess angle sum. So we're saying that if we have, alright, let's look at it like this. If we have a square, we have 4, so n would be equal to 4 here. And then we draw a point that connects all of them, right? So we can go like this one connects to this one connects to this one, and this one connects to this one. So with the 4 points, and they have an origin. So from the origin, we connect to all the other 3 points. And what do we get? We get that this one has 1 and 2 triangles, right? So we say that each triangle, when we find a triangle, that's equal to pi. So now there's 2 of them. So inside of the square, we're going to have 2 pi. So the sum of this, right, because there's 1 pi, there's 2 pi here, right? Because that's, so these three angles add up to pi. And then we get another one, and that also adds to pi, so the sum of them is 2 pi. So instead of a square, we get 2 pi. What's interesting is that it doesn't have to be regular. You can have any 4 points randomly scattered like this. Random, not regular. And do the same deal of just connecting, and we still have 2 triangles, right? So the amount of numbers, the amount of points it has, the polygon, we know how many pies it has, how many circles it has, how many parts of the circle it has. And we know that each triangle is half a circle. So when we're flat, the sum of the angles of a flat triangle are going to be half a circle. Pi is equal to half a circle. Okay, so we understand this a little bit now. We see that, well, let's see one more example of this shit. Alright. And then we're going to go into sort of why the two of them are different, I guess. Alright, let's do it now for the pentagon. Dude, I am sorry if this is bad. You don't have to watch this if you're enjoying it. I'm glad. If you're not, well, I'm sorry. What are you going to do? I'm trying, man. Really, I'm trying. This is what quarantine is, right, I guess. You got to hold your abilities. Alright, so we have a pentagon now. So this is n equals to 5, and we're connecting all of them now. So now we have 1 triangle, 2 triangle, 3 triangle. So we get that the sum of them, so inside of them, is going to be 3 pi. So when n equals 5, we get the 3 pi. That's the sum of the whole thing. And remember, they don't have to be regular. We can have any 5 points randomly scattered like this, and we still end up with the 3 pi. 1, 2, and 3 pi. It doesn't have to be regular. We still get the same angle summation, whatever points we have. So this works. Now you might be realizing a little bit of a formula, right? So we're saying, so here's the list of this shit. So we're saying that when there's 3, there's 1 pi. When there's 4, there's 2 pi. When there's 5, there's 3 pi. So I think you can see the pattern, right? So when there's 6, there's going to be 4 pi. When there's 7, there's going to be 5 pi. So if this is n, and I guess this is just the sum of the angles, we see that the sum of the angles is n minus 2 times pi. So this is n minus 2 times pi. And that's the sum of the internal angles. Now, in the case of regular polygons, this interesting thing happens where all the angles are the same. So when it's a regular polygon, this angle is the same as this angle, is the same as this angle, the same as that one, the same as that one. Why this is interesting is because then we can simply take this amount and divide it by how many sides it has. So then this angle is going to be equal to 3 pi over 5. If we, then that's the angle. I mean, that is the angle. That is an accurate description of this angle. Now, let's say that you wanted like the half of it. Let's say that we have, take away some information here. Let's say we had a center, and then the line that goes through it, hits it, goes through it, hits it, through it, hits it. It's like that. And now you don't want the full angle. Let's say now you want this little guy. Now you want this little guy right there. So how do you get it? It's going to be half of this, right? We can multiply this by a half. We can multiply this by a half, and we would get simply 3 pi over 10. Would it be? No, would it be 6 pi over 10? No, because then it has to be, so we're saying that it's now over 10, so it's 3, 6. This has to be then 4, because that's the sum of the angles, so 3, 3, and 4, is this 4? No, it has to be 2 pi over 5. So this is 2 pi over 5. Or 4 pi over 10. Yeah, so it is. So then this little guy right here is 3 pi over 10. So then we can also like think about that what denominator is being used in the fraction. So if we have a 10 in the denominator, then these angles add up to 10. So we're having 3 here, we have the 3 here. So which number are we missing? Right? So we're saying that 3 plus some other number is going to be equal to 10. Pretty simple stuff, right? We simply, move this shit around, and we get, we can get this like 6. So x equals to 10 minus 6, so that's 4. So then x equals to 4. So then we have here that this is 4. And 4 what? That's 4 pi over 10. This angle. So 4 pi over 10, 3 pi over 10, 3 pi over 10. So we're using now the radians and the fact that we can sort of divide it. How to get this 4? We can also think of this as being a circle here. And then this is being a 2 pi. We're dividing it in fifths, so this is going to be naturally 2 pi over 5. Double that, now you get 4 pi over 10. So we're saying that, 4 pi over 10 is equal to 2 pi over 5. So these two are the same thing, and that's that angle. If you wanted to convert it to degrees, you can. All you have to do is multiply pi by 180. That's all, if you want it to be like that, right? So it's a nice little list, and of course it goes on forever. Now, but here's another interesting thing. So the angle sums, all right, so wait a minute. I know I'm all over the place, and I haven't gotten to Islamic patterns quite yet. But we are sort of moving along. I feel we now have an understanding at least of the fucking, what the shit. Yeah, this thing is getting dried because I'm using it. I'm not covering it too much. Let's give it a little rest here. Let's see if this thing, with a little rest, gets back its thing. So we're talking about angle sums, are we? Okay, now we're going to talk about star polygons. No. We're still, star polygons are a little bit too complicated still. We gotta talk about tilings. So there's two different words here. There's tilings and then there's tessellations. You might think they're interchangeable. Tessellations, I don't even know if there's two L's there. I think it's only one L. Things like that, tessellations. So these two are not the same, strictly speaking. Tilings is when you're moving regular polygons around. So tilings involve regular polygons. Tilings involve regular polygons. Involve regular polygons, and tessellations don't. Sorry for my writing. Tilings involve regular polygons, tessellations don't. So that's pretty much where we're at. All right. So where we're at is that we have the Schlafly symbols. And so yeah, we're going to talk about tilings. So tilings. All right, so we have the Schlafly symbols, right? We have, so if I say like this, so brackets 4, so I'm talking about a square. Now, if I say bracket, comma, 4, I'm saying there's 4 squares around the point. So I can take any point right there, and I'm saying that there's going to be 4 of them. So there's now 1, 2, 3, and 4 squares. 4, comma, 4. You can also write this one as 4 to the power of 4, or we can write it as 4.4.4.4. All these three are the same. So 4 comma 4 is the same as 4 to the power of 4, and is equal to 4.4.4.4. 4 fours is like this. And a single square is like this. And yeah, so we can break these down. There's only going to be 3 what we call platonic solids, platonic, not solids, platonic tessellations, platonic tilings, I'm sorry. There's only going to be 3 platonic tilings. So there's 3 platonic tilings, and I think there's 13 Archimedean tilings. So the 3 platonic tilings are of course, the 4 comma 4, just a grid of squares. We have the 3 comma 6, which is just a grid of triangles, and we have the 6 comma 3, a tiling of hexagons. Now, what makes it platonic is that we only use a single type of polygon. But once we include another polygon, then it becomes Archimedean. So that's the distinction of it. So, you know, it's kind of fun to do this kind of thing, because we can also, it could be like this. So there's going to be that point, and then this one's going to look a little bit something like this. It's going to be that point, and then this one is going to be looking a little something like this. So there you have your 6 triangles, there you have your 4 squares, and there you have your 3 hexagons. Notice that these 2 are interchanged, right? These 2 numbers are, turned over on both of them. That means that these are dual, and that the 4 is self-dual. You can just rotate these and we get the same deal. This is self-dual. This is, I think this is very Kepler. Kepler does this thing with the duals, and these 2 are dual. So these 2 are dual. So what this with the duality means is that if we had points on the center of these shapes, so point here, point here, point here, and we connected them, we get the other tiling. So we have points here on the center and we connect them. We get now a hexagon. So, you know, these two are, and we have here some points on the center. So that's what it means by self-dual. We get another grid of squares, here we get a grid of hexagons, and here we get a grid of triangles. Underneath it, right, we connect the centers. So this is the duality aspect of it. So there's only going to be 3 platonic tilings. I think there's going to be 13, or maybe it was 15 Archimedean tilings. And let's go a little bit over some of them. Now, we have the advantage of foresight, and we can sort of mix it up a little bit. So let's look at this one. And again, this is because we have the advantage of foresight. So this is a pattern we can use. So this one is using, so we say here, so what will this one be? So we have a square here, so that's a 4. Then sort of we're moving around the circle, if you will. So first we're counting here, and then we can move clockwise. We can move counterclockwise, it doesn't really matter, it's the same thing. So we have a 4, and then we have a, so 4.3, 0.3, 0.4, 0.3. So this is the description of this tiling. 4, 3, 3, 4, 3. 4, 3, 3, 4, 3. And we can start to count anywhere. We can still get the same sort of, same configuration. We can start to count in this 3. So we can say the 3, 4, 3, 3, 4. And it's still the same thing. It's just a matter of where you start counting. Interesting about this is that we can also see that at this point, we can draw a circle in it. So that means that the sum of these angles, of these 5 angles, is going to be equal to 2 pi. Further, because of the internal angle formula, we could establish the sum of these angles. So because it's a square, for instance, we know that the square is going to be, well, what is the internal angle of the square? So we said that's a square, so what's that? So we know that the sum of them is going to be 2 pi, and then this one's going to be 2 pi over 4. Pretty much, that's what this angle is. We can, the denominator and the numerator have a common denominator, have a common factor of 2, so we can write this as pi over 2. So we can write that down there. Dude, I've gone over this so many times. But this is fun, right? So this is what I'm saying. I'm saying that the sum of these 5 angles is going to be equal to 2 pi. Now we need a common denominator for this to work. We can simply take it up to 6. These have a common factor of 6. So we can take this as 3 pi over 6. Well, all of it over 6, right? So it's just 6 underneath and just all of it. Let's just go ahead and convert it over here, down there. So the 2 is going to be a 3 plus a 2 plus a 3, no, plus 2 plus 3 plus 2. Pretty much, right? So 3, so these 2 are 4, these 2 are 6, this is 2, so that's 12. So this is equal to 12 over 6. 12 what? 12 pi over 6. 12 and 6 have a common denominator, a common factor of 6. So we can just simplify that and we get 2 pi. So it's kind of fun, you know, to try and like get the common denominator, get the common numerator, just, you know, get the common factor and get that all of it and, you know, try to comprehend these patterns and sort of why the sum of the angles might work in a flat way and etc., etc., etc. Interestingly enough, we can sort of jump now, I guess, to solids. I guess, maybe, I mean, where am I going with this? I don't know, it's just all these stuff is just in my brain, man, I don't know. Alright, so we're talking about tilings. We've gone over one of the Archimedean. We saw 3 platonic so far. How about we see another real quick Archimedean, one that's off the top of my head here. So this is going to be an equilateral triangle. This is going to be a hexagon. Now you might notice that this hexagon could be interpreted as 2 triangles, since we have, you know, we have this, we have that, and we have this, then we get the same deal. But we're looking at it more in terms of a hexagon. So what will this one be? This one would be a bracket 4.3.4.6. I'm counting clockwise. I'm going 4, 3, 4, 6. Then it goes back into 4, so that's where I stop and close my brackets off. So then this tiling can be described as this. We can do the same thing with the angles and whatnot. But it's interesting to think about that this possibility, this summing to 2 pi, is what makes it possible. So then it becomes a matter of, well, can I make a list of the internal angles of my polygons and combine them in different ways that I end up adding up to 2 pi? And what happens if I add up to less? Right? Because then that's where sort of where the solids comes in. So if we look at a fucking thing like a cube, like that, for instance, take away the excess, the thing that's not sort of, you know, visible, we take away the 4th dimension, if you will, the 3rd dimension, sort of looking through, we see it like that, and we look at a vertex, and then we see that, well, that's a 4, that's a 4, that's a 4, so we can say this is a 4, comma, 3. Right? So we're saying that there's 3 squares on every vertex. So then this is what we call a hexahedron, or a cube, the 4, 3. So then we can see how, you know, we take away 1, so it's almost as if we had, you know, this grid, and we simply took away 1 by folding. We could actually fold this and then connect these two, we would get this angle. But by a fold, no? You just put that over there. Alright, so we can see how the Schlafly symbols have that reach, whether we can actually use them to describe solids, we can use them to describe tilings. Pretty powerful stuff, the Schlafly symbols. And so one more thing I wanted to talk about, I don't even know, dude. Should I check the comments and then like get some feedback as I'm going with this? No, let's just plow through it, man. Just plow through it. Alright, so star polygons. So the star polygons sort of work within the scheme of the Schlafly symbols. They also operate within the brackets, and we have here, so I write it as n/k. This is how I personally write it. And I'm sorry with the brackets, I tell you, I suck at drawing. n/k, that's sort of my way, my takeaway on this. So let's try and talk a little bit of what k is. So if we have, let's say, so we're saying that again, when we write this, we're talking about circles. We might be talking about polygons, but we're really talking about circles. So let's go ahead and draw an example. So let's just up this list. Let's just go up the list as we move along. So let's just write in, right now, I'm going to write in this right here as my n equals, and I'm going to just change it up as we move along. So we're going to start with n equals 1. So it's pretty much that. So nothing's happening. And then we write n2. So then there's 2 points on the circle. And then here we might write that k, right here. K is a line, right? So we can write here that k equals 1. Now why? Well, because we go 0, and then 1, and we can draw a line. So that line, that exact line, we can write it as a 2/1. Now, because 2 over 1 is simply 2, we can write this line, I'm talking about the line, as 2 inside of the bracket. Because 2 is the same as bracket 2/1. So these two things are the same. And that's the line. So let's go up the list now. So now we're going to go, oh shit, I forgot. Yeah. Okay, so I'm going to leave these in. So now I'm going to write in n equals 3. So now we have these 3 points. And again, we can connect that line like that. And then that's also going to be k equals 1. So then this polygon is the same as with the 2. And that it's simply, you know, the brackets 3 is equal to 3 over 1. Same deal, same thing. Nothing special so far. I mean, we're just describing polygons. When are we going to get to the juicy stuff? Alright, let's go to some juicy stuff, right? Alright. So let's move right ahead. We got to plow through these numbers, man. Otherwise, we don't learn. So we can take that, take that, take that. So now we have 2 numbers in the system. So we have here n4, and k could be 1 or k can be 2. If we write in k1, so we go 0 and then 1, and then this is our new point, so then this now becomes our 0, and this now becomes our 1, and then this becomes our 0, and this becomes our 1, so the 0 is the origin, so we go 0, 1, it's like backgammon, right? You go from where you're at to the next one, so 0, 1, like that. And it goes on, right? It's just a little system which can be described, so this system can simply be described as like that. But if we write k4, k2, 4 over 2 like that, well, we get they have actually a common factor, don't they? So what we do is, well, let's write it down. So we go 0, 1, and 2. And then that closes, we can write, because if we go again for this 0, 0, 1, and 2, so it repeats. So we have 2 points still missing, so we gotta like lift our pen up and go to the next one, so we go 0, 1, and 2. So then this is equal to these 2 lines. Interestingly enough, so what we do when we have a common denominator like this, we take this number and we put it outside. And then we leave the solution for that out. So we take this denominator, we put it outside of the bracket, and now we end up with 2 slash 2, actually. So these 2 lines can be described like this. This never comes up, by the way. This never ever comes up in the literature. They don't ever write it like this because these things are taken for granted because they're not graphically interesting. Or they might be some sort of redundancies, right? Yeah, that tends to happen quite a bit. I'm going to erase the whole shit. I'm going to write in one more circle. I'm going to see the first star. So the first star comes in the form of a marker that doesn't work. If anybody knows how to make these markers work better, let me know. In the comments, I should be reading. Alright, so we're circle now. So now we've got to go to n equals 5. So you might have noticed that before we didn't go over half of, so we're going to get into that a little bit. So what can k be if we have n equals 5? So 1, 2, 3, 4, and here's 5. Yeah, since 5 points, we're going to, of course, suppose that they are equidistant. The bracket makes them equidistant in concept, right? So we go in for the 1, we get a pentagon. So this one is this one, pretty much, you know. And then we get a nice little interesting thing that we can actually write a star. So we go 0, 1, 2, goes like that, and 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, like that. And then this one is the 5 slash 2. And that's it. I mean, we don't have a 5 slash 3. I mean, okay, so let's go ahead and think about that. What would happen if I said 5 slash 3? What would happen to that? So we can go 0, 1, 2, and 3. Oh, we already have it. Alright, then we go here, and we're counting clockwise. So 0, 1, 2, 3. We already have it. So 5, 2, and 5, 3 are the same. Now why is that? Well, it happens to be because there's actually sort of an invisible mirror that goes right between it. So after it crosses your mirror, so if it goes 0, 1, 2, once you cross your mirror, you're going to repeat the thing. So there's a rule for k that k has to be less than whatever n is. Half of it. So it has to be less than half of it. So we get a nice little first rule for k. So we're saying that k has to be less than n over 2. No, that's more. Like that. And we're also saying that, well, because it's sort of redundant to say that, you know, k equals 1 is a polygon. To get that out of the way, we can write that n has to be more than, k has to be more than 1. Because when k is 1, we don't write 1. So we can have these two rules. K has to be more than half of n, k has to be more than 1. Less than half of n, k has to be more than 1. And so we can write these little systems as we move along, and we can get our star polygons. And so that's sort of where that comes from. We can compound them, and we can sort of play around with them and stuff. And so we gotta look at one more star polygon to get like the full picture. So we see here the first star polygon, and now we're gonna look at the first compound star polygon, and that's in the 6. So this is gonna be n equals 6. And then what's k gonna be? Well, we have our rules for k. K has to be less than half of n and more than 1, so we're gonna avoid writing the 1 anymore. I mean, we can, but you know, it's a given, so whatever. So we can write 2. That's it. That's pretty much it. 1 and 2. I mean, 1 just being the polygon itself, right? But I think it's very useful to not get our minds off of the fact that we're talking about a circle when we write the brackets. So let's write that down. n/2, and only n/2. We're not going to write in the k equals 1 bit. So we go 0, 1, 2, 0, 1, 2, 0, 1, 2, and it closes. So we have a closed system here. We got 3 points left over. 0, 1, 2, 0, 1, 2, 0, 1, 2. So we have here a compound star polygon. The 6 over 2. We can take the denominator, put the denominator outside of the brackets, leave the result of the division inside, and we get a 2, 3. So the 6, 2 is equal to 2, 3. 6, 2 is equal to 2 triangles. A hexagram is equal to 2 triangles, as we can see here. This actually is a symbol, of course, people associate with the Star of David, but it actually has more to do with the integration of opposites. We see here we have a triangle facing upwards, we have a triangle facing downwards, and they are interrelated. So this is like a marriage. This is actually the symbol for marriage. Sort of like the female and the male coming together, right? Yeah, sort of if you want some mystical thing in your geometry, there you go. And you know, we can take this up. As we move along the list, of course, more stars are going to come up. Naturally, as we move along, more stars come up. But before we go into whatever it is I'm going through, I want to write more about the radians. So I want to combine now star polygons, and I want to include the radians. So star polygons and radians and U. Star polygons, and I don't know how to do the thing, that symbol for the end, and this shit is not working. Yeah, well, star polygons and radians. This is actually a little helpful to understand the angles like these patterns might come up with, like what is this angle, what is that angle, what is this angle. And we can use these systems to understand which angles there are, and we can do analysis of the patterns. We can try and figure out what it is that's happening. It's a lot of fun, it's very interesting. So star polygons and radians. All right, so we were saying that, or we had a list that, if we have n, then the list over here of the internal angle formula is going to be n minus 2 times pi, right? So it goes, kind of pretty much goes. What's interesting is to think also about the possibility of star patterns. So it actually becomes interesting if we combine those two things. So let's say we go into the hexagon once more. So this angle, according to this thing, so we have a 6 here, then this thing is going to be a 4 pi. And what we're saying is that we're going to go actually sort of like, 0, 1, and 0, 2 over here, then 0, 3 over here, then 0, 4 over here. And we have 1, 2, and 3, and 4 triangles. I want you to notice that if we take away this middle line, we're not going to take it away, but we might sort of understand it to be. But if we have these two angles, sort of like this whole deal right there, what is that? So that's 2 pi over 6, or equal to pi over 3. So we can take away 2 pi from any star. So if we have the internal, we take away 2 pi, and if we have a leftover, that's a star angle. So the star angle for the hexagram is pi over 3. You might be thinking, well, what does that have to do with anything? All right, so let's go ahead and just see this example with a pentagon now. So we say that n equals 5, n minus 2, that's 3 pi. Can we take away 2 and still have 1 left over? Yes, we do. If we take away 2 from this, we still have pi. So how does that look? Looks a little bit something like this, right? 1, 2, 3, 4, 5, like that. All right, cool. I'm feeling the energy now. I feel euphoric. This is why I do this. This is why maybe I should have some breakfast before I do these kinds of things. But it's fine, whatever. I'm young. I don't care. So it goes a little bit something like that, right? So we have 1, 2, and 3, and we're saying that, you know, this happens to be the 5, 2. You can complete the pattern, of course, but then the question is, what is the angle of the pentagram? Just happens to be the 3 pi, we take away 2, and then this is going to be pi over pi. So the internal angle of a pentagram is going to be pi over 5. Interesting. We're taking away 2, that's what we get. So what if we upped the number? What if we went a lot higher? What then? How many stars and what angles are going to be there? It's a fun game, man. It's a fun game. I like it, man. We can take away 2, we get more stars. And also we can write this, so this is sort of like when k equals 1, and then this is sort of like the case when k equals 2, so then this would be like 5, 2, and then here's going to be the pi. So this is more like sides, and this is the angle. So the pentagon, 5, 3, the pentagram, pi over 5, I'm sorry. So 3 pi over 5. 3 pi over 5, pi over 5. Nice, right? It's cool. So what would happen if we add another number to the list? Alright, well, k stays the same. I mean, as we move along. So what should we get? What should we get? Well, let's put an 8. Let's put in an 8. So what's the angle for an 8? Well, we have, it's going to be 6 pi over 8. And then when k equals 2, we have the 8 / 2. Of course, all of these are inside of brackets, of course. We drop brackets so much. So we take away now 2 pi to this, so it's going to be 4 pi over 8. And wait a minute. Well, actually, no, this is not written with brackets, actually. This is, but this isn't. I'm sorry. So yeah, 4 pi over 8. Wait a minute. We can actually simplify this. We can simplify all of them, because they're all, you know, what do you say? They're all factors of 2. But let's keep this going. So we have 4 pi over 8. You might see the pattern a little bit. You can still keep on going. So we have a k3, because this is less than half of this. So n/3, and we have here 2 pi over 8. So for the 8, 3, so if we want to draw these, this is the one that goes a little bit something like this. So I have to write my points. This will something like 1, 2, 3, 4, 5, 6. And then this one goes a little bit something like this. And then this one goes a little bit something like this. Octagon, octagram, 8-2 octagram, 8-3 octagram. You might also notice that the 8-2 is inside of the 8-3 and that the 8 is inside of the 8-2. So all of them contain each other. And also we can construct them by an extension. We're not going to go into that right now. But, so this angle is this angle. And this angle is this angle. And this angle is this angle. So that's a fun little system, isn't it? It works really well in that we can take away just 2 pi from all of them and we can get the exact angle of our stars. No need to start counting like how much 360 is this and shit, fuck that. We simply stay with the elemental, with the basics. So I think that's cool, I think that's nice, it's, you know, it works. And one more thing we should talk about is then, I guess, Islamic patterns, isn't it? We gotta talk about Islamic patterns. How does all of this connect? Well, it depends on how you look at it. It depends on how you understand circles and how you understand polygons. And maybe perhaps you can understand them as a combination. So you can perhaps understand the square, let's say. And we can have these points be circles, let's say. So here we have a 4, and then it becomes, well, actually, before we go into this, there's one more thing that I remember now. So we have to connect the radians with the fullness. So we got to connect radians, and we got to combine them with the fullness. So radiance and fullness. So all right. We were saying that the fullness was this interchanging of color. We go from the black, you go to the red. How are we doing on battery? I don't know. Let's hope that this thing is still going. I don't know, man. Shit. All right. So, okay, radiance and fullness. So we're saying that if we have a circle and we have this interchange, this sort of one line then becomes another line. And so let's take the case for threefold. What is this angle? Because again, remember, this is threefold because from the center we change colors. So this one's going to be one color, then this one's going to be another color, and this one's going to be like if you fold origami, you might be like, wait a minute, that's a mountain, that's a valley, or backwards. And that's exactly right. That's what's so cool about this, that fullness and actually folding paper do combine really well in this structure. Okay, so what angle is that though? For this threefoldness. So this is a threefoldness. What angle is it? It's pi over 3, man. Whatever number you have in your foldness is pi over that. You can try it. You can try it with other numbers. So whenever you say like, oh, that's a 12-fold pattern, what are they saying? Right? Actually, we're not going to go into 12 because that's a lot of lines. Actually, 24 lines for the 12-fold pattern. For a proper 12-fold pattern, you need 24 lines because it's double of that, right? Let's go into 4, I guess. Ba, 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 ba. So this is a 4-ness. It's a 4-fold. And the question is, what's this angle? Well, that's pi over 4. Because we're 4-fold. And we can understand these as interchanged. Right? Well, that angle for the 4-fold is pi over 4. What the full number, pi over that. So that's a cool way of understanding what you're working with. Just say a number, fold, and then just put that on the pi. And that's the angle you want to work with. That's cool. You don't have to think about 18 degrees, 36 degrees, 54 degrees. Nah, just that number, pi over that. Remember, pi is equal to 180. So if you wanted to actually find the degrees for it, you say pretty much 180 over 4. Pretty much that's what's happening. Let me get that, that's 45 degrees. If you wanted to. I prefer this method because you can get to crazy numbers without having to use some crazy numbers over here. So what would happen if we go 7-fold, right? I mean, 180 degrees over 7, that's something. That I don't even know what that is. It's something, it's not irrational, but it's just, we can express it, but we can, I don't know, why? We have this system, especially because we're just combining circles. Okay, all right, so the stars work inside the circles, the fullness will work inside the circles. So where does that leave us? All right, so let me look at my notes here. We talked about the tilings, Schlafly symbol, that's covered. Okay, so we should talk about some of the basics of the Islamic patterns, I suppose. So we're not going to go too deep here. This one can go like so deep, but I'm going to try and keep it real light, real simple. So I'm going to get a square going on. I'm going to divide each of these corners, not the center, the corners. So that's sort of where my lines are going to meet. All of these are going to be 4-fold. So 4, 4, 4, and 4. So I'm saying that this one goes up to there, this one goes up to here. And that's pretty much nothing, so let's say that now we're going to go up to 8. So we're going to put an 8-fold division on all of them. So all of them are going to be 8 divided, so this one's going to go like, and this one's also going to go, and they meet. You might recognize this. This is something that looks a lot like an origami pattern, and you're right. But, not going into where they meet, actually that's not important. What is important is where they're meeting here as well. They're meeting here in the middle. Actually, if we folded this, we might want this line. It's a lot like an origami pattern, doesn't it? Let's put a circle that has this as a radius. On all of them. Now, let's install a star. Oh, there's one more thing about stars that I didn't get into. I'm not going to go into it right now. There's one more thing about stars that just makes folding them so easy and so cool. Not going to go into that though. We have a circle. We have points that connect on the circle. What do we do with the points? We put stars inside. What else, man? Well, we might notice that these points are points of contact. So what if, and I'm just saying what if, we installed points at the contact that go into each other? So that is to say that what if we inscribed here an 8-3 pattern? So it kind of goes like this, wouldn't it? And this one will go like this one will go like this, and then no, this one actually would go a little bit more like this. And this one would go a little bit more like that, I suppose. This one would also go a little bit more like this. Yeah, that looks about right. So with a little bit of cleanup, we get that, and then this one can go on. Take away this, we can take away this guy, take away that guy, take away this. So I'm installing an A3 here, and I'm installing it at the points of contact. And so we can keep this going. Goes like this, goes like that. This one goes here, extends, extends, and we have a little star that happens here. We can clean it up. And you can choose, right? You can choose which star you want to put into the thing. Of course, if I was folding it, it would just be easy because all you need to do would be to fold all these into a single square and then just fold a star and then you're golden. You don't even need to do anything. Actually, I might demonstrate this live. I want to, yeah, let's fucking do it. Let's do it. All right, I'm gonna check the comments if this thing is working. Dude, I'm sorry for this. Oh, you can't even see anything now, can you? Well, it might look better on once it's recorded, I guess. All right, so we have this. We move that up to here. So pretty much I have a square, just like I have in the example. And I'm going to fold here a 8-fold division like so. So just a little bisection of it, because it goes from 4, half of it is 8. So simply a bisection here. This format was not the best. I understand that with the comments it just doesn't make sense. But once it's recorded, the comments go away, so I'm hoping that that makes it better. And so I'm just going to keep folding this thing. And then this thing right there. And so I have one of these quarters. I have here my 8. And now all I need to do is inscribe my 8-3. So it's going to look a little bit something like this actually. Where this point is going to line up to that line. Combine it with that one as well. And then what I can do is I can simply take my divisions here, combine these with that. You can see that actually that lands right there. So that's cool. This one would land on it as well. It does land on that point of contact for this one. This one must land on that point of contact for that one as well. And pretty much that's pretty much set up, you know. I mean, that's it. All I need to do now would be to cut it. So let's see if I have some scissors here. Or you know what? I just really open it up and just inscribe on it. I did have a pen that's not meant for this thing. Where is it though? Might have taken it away. Anyway. So you see here how the H3 put on a single corner can be then copied to all the other corners. And we get this very basic pattern, very cool pattern, but you know, it sort of suggests the idea that you only need to inscribe on a fourfoldness. So this is a fourfold pattern, right? Because it's just divided onto this division. It's 1, 2, 3, and 4 divisions. So the pattern is actually located within a fourfoldness. So it's a fourfold pattern which has an 8 character. So we're going to leave it at that for now. And before I leave, I wanted to thank my Patreons here on Patreon. So if you want to support this kind of content so that I can get better at it, so you know this thing becomes not so tedious, you can go to Patreon, but I wanted to thank them personally. So I want to thank Alenka Plauder, Bridget Schilling, Folderia, Sarah Gelser Brewer, Shashi J, Anurag Agarwal, I'm home pronouncing that right, Fatme, Irina, Jeannie Halaba, Mimasa Baya, Natalie Simeon, Peter Keller, Surabi Koshar, Uzma Sayed, Amit Hindosha, Hannah Lubner, Heidi C, Rui Kershi, and Shramina Hacks. So thank you all. These are the Patreons. Thank you all very much for your support. If you want to have more of this type of content, again, go over there. Hope you have a beautiful day. Thank you so much if you watched. If you didn't, well, we got to keep it going better, so I might return to this thing. And yeah, have a fantastic day. I'll catch you in the next one. Take care. Bye-bye.